Hello everyone. Today we will solve a problem on design of box culvert. So let us take one example. The example is shown on your screen now. Design a box culvert having inside dimensions 3 meter by 3 meter. That is, inside the clear vent is 3 meter wide and 3 meter deep. This culvert is subjected to a dead load of 14,000 Newton per mm square. So dead load here is given and a live load of IRC class AA tracked vehicle. So dead load here is given. IRC live load we have to calculate based on IRC class AA tracked vehicle. That is an army truck. Assume the unit weight of soil to be, that is density of soil here is given 18,000 Newton per meter cube. The angle of repose of soil is 30 degrees. He is given angle of repose of soil to calculate the coefficient of active pressure or passive pressure due to soil on the side walls of the box culvert. So use M25 concrete and Fe415 steel. Road width of 7.5 meters. Span 3.3 meters. So road is of 3.3 meter span. Width is 7.5 meters. That means your box culvert is of 7.5 meter. 3.3 meter, the 3 meter by 3 meter vent is for 7.5 meter length. That is across the width of your road, your box culvert spans. Okay. So we'll consider out of 7.5 meter length, we will consider 1 meter length and we will design it for per meter length. We will calculate per meter movement, per meter length, the steel, everything, and the same reinforcement we will provide for the box culvert. Now, for our design purpose, 1 meter length of box culvert is considered. Analysis is done for 3 critical loading cases, which I have explained in the previous class. So out of 3 critical cases, for first load combination, I will explain it to you here, how to design it. For second and third combination, you take it as assignment. For first load case, we will design the box culvert. The first load case is dead load plus live load plus soil pressure from outside and no water pressure from inside. Okay. Now we have 3 meter by 3 meter box culvert. So first I need to fix the thickness of slab for your box culvert. Thickness of RCC part I have to calculate. So thickness of the slab and walls are assumed as 300 mm. This thickness is normally taken as 1/10 to 1/15 of the span. So if it is of 3 meters, 1/10 of the span means 3000 by 10. That gives you 300 mm, right? So it is assumed as 300 mm. Bearing coat thickness is assumed as 80 mm on the top slab of the box culvert. For analysis, the central line of the frame is considered. So 3 meter by 3 meter is the dimension of the inside vent. The frame dimension will work out to be 3.3 by 3.3 from center to center. Now RCC or slab thickness and wall thickness of box culvert has worked out to be 300 mm. So it will be 3.3 meter by 3.3 meter. Okay. Now, so first load case I will consider dead load, live load acting from outside while no water pressure from inside. Concentrated vertical load owing to wheel first. Okay, so 6 load cases I have explained in the previous class. So in that I will not consider the water pressure from inside. So from first I will start. First one is concentrated vertical load on the top slab, that is the wheel load, right? So that is W is equal to P I by E, or you can call it as E, you can call it as B effective. Anyhow, E is what? Small e, which I have explained in the previous class. It is the width of dispersion. You can also denote it as B effective. Effective width of dispersion for a single load is, so as you have designed in the slab bridges, B effective is equal to alpha x 1 minus x by L plus BW. So B here is 7.5 meters width of your road. L is 3.3 meters, that is length of the road. Okay. B by L is 2.27. Based on this, referring IRC 21, I will calculate the alpha value. Now calculate the width of dispersion. That has worked out to be 3.155 meters. Net effective width of dispersion for the tracks after allowing for the overlap is 1.2 plus 0.425 plus 2.05 plus 3.155 by 2. After allowing for overlap means we have width of 7.5 meters. Width of the road as 7.5 meters. Along the width, if you place your vehicles, 1.2 is your C distance, 1.2 your C distance, 0.425 plus 2.05 is the center distance, and dispersion width of 3.155 by 2 on other side. Okay, so place the vehicle and check it. Place the vehicle and check it. See here. So this is your box culvert. Along the length, if you draw the width of dispersion diagram as you have drawn in a slab, as you have drawn in slab bridges, okay, 1.2 C distance, right? After that, 2.05 from center to center of the wheel, 3.155 by 2. So total width of dispersion 5.26 meters. Effective length of dispersion is 3.6 length of the vehicle plus 2 times the thickness of the slab including wearing coat, that is 0.08 meters, that is 4.36 meters. So this length is greater than actual span available. So length of dispersion means we have the box culvert effective length as 3.3 meters. So here length of dispersion I am getting it as 4.36 meters. That means vehicle is going out on both the sides. So if your class AA tracked vehicle is standing on the box culvert, it goes out on both the sides because 3.3 meters is only your box culvert, right? So I have to consider only the load of the vehicle along the length which is acting for 3.3 meters, not which is acting for 4.36 meters. So I will calculate the reduced load because on both the sides vehicle is going out of box culvert, though that much of load I will neglect. So reduced load is 700 kilonewton, that is the weight of IRC class AA tracked vehicle, 3.3 by 4.36. So 530 kilonewton only I should consider. Now load with impact factor. So impact factor of 25% is there for class AA tracked vehicle. You can check IRC 21. So 662.27. So intensity of live load is here PI by PI 662.27 divided by V effective, that is 3.3 into 5.26. 3.3 into 5.26, that is width of dispersion and length of dispersion will give you area of the dispersion. Intensity of live load on the slab is 37,000 Newton per meter square. Next, loads and reactions. Dead load of the top slab. 300 mm is thickness, 25,000 is density of RCC. It will give you 7,500 Newton per mm square. Total load on culvert is now dead load plus live load. So dead load he has given you as 14,000 Newton per mm square here. 14,000 Newton per mm square he has given, which is acting on the box culvert. So 14,000 plus 37,000. This one is 51,000 Newton per mm square. Dead load plus live load. Now, therefore, total design load on top slab is 51,000 plus 7,500. 51,000 plus 7,500. 58,500 Newton per meter square. Now, concentrated weight of each side wall. It is of 3.3 meter in length vertically. Okay, and 300 mm thickness, density of RCC, that will give you 24,750 Newton per meter. Upward soil reaction. So once your box culvert is rested on the soil, okay, due to the load which is coming from above, it will exhibit some upward reaction. It will exhibit some upward reaction. That is 58,500 into 3, 58,500 into 3.3 plus 2 walls. It is 2 into 24,750 divided by 3.3 into 1 meters. That means total load which is acting from the top, that is 58,500 into 3.3. Okay, plus due to side wall 2 into 24,750 divided by the area per meter square area or at the base, that is 3.3 meter width and 1 meter length I will consider. So it will give you the soil pressure acting from the bottom. So this I will be marking it in the figure. First see here. So I am marking it in the figure. From top, you are getting 58,500 Newton per mm square, Newton per meter square. From side wall, on side walls, you are getting the soil weight that we will calculate now. Okay. So due to all this load, I am getting the upward pressure of 73,500 Newton per mm square from the bottom. That is, soil is exhibiting the pressure. So we will calculate now the weight of soil on the side walls. So here, coefficient of active earth pressure now. We have seen the linearly varying load due to soil on the side wall is W into H multiplied by coefficient of soil pressure. That may be active or that may be passive. Now it is acting from outside. It is active earth pressure. That is one minus angle of sine of angle of repose divided by 1 plus sine of angle of repose. He has given you the angle of repose, that is 30 degrees. So it will give you 1/3. So lateral pressure owing to dead load and live load is total vertical load into Ka. Total vertical load we have is 51,000. Total vertical load we have 51,000 to 1/3, 17,000 Newton per meter square. So lateral pressure owing to soil is Ka into W into H. 1/3 of density of soil 18,000, that is 6,000 Newton per meter square. So lateral intensity at top is 17,000, lateral intensity at bottom is 17,000 plus 6,000 into 3.3. So that I have indicated it here. So lateral intensity at top is 17,000, at the bottom it will become 36,800. Clear? 36,800. It is this one at the bottom. Now, how to calculate the moments and shear force? So I will consider it, since it is a box culvert, I will consider out of A, B, C, D, I will consider half portion. I will consider half portion of it. That is, I will consider one junction, that is D. From D, it is A, and from D it is C. We will get two parts of the box culvert. Next, if I consider the junction A, I will get two parts, that is AD and AB. Two parts of the box culvert I will get it. So these two junctions I will consider it as a continuous beam and I will apply moment distribution method for that. Okay. So to apply moment distribution method, I need to calculate the distribution factor and the fixed end moments. Right now, relative stiffness for the members are, see here, distribution. You must have studied the moment distribution table, moment distribution method. Joint member at D we have DC and DA, at A I have AD and AB. So distribution factor 1/3, 2/3, 2/3, and 1/3. You have calculated it in moment distribution method. Right now we will go for the. So these are the distribution factors. So you have studied it in the SA2, right? Now fixed end moments. Fixed end moments MFAB, that is WL square by 12. So W I have 58,000 into L square by 12. MFDC plus WL square, that is clockwise, anti-clockwise. Right? MFAD now WL square by 12 plus WL by 15. MFDA WL square by 12 minus WL by 10. That again same equations, clockwise and anti-clockwise. So I will calculate the fixed end moments like this. Okay. So on the top slab AB you have only UDL. That is why I have considered WL square by 12. So on the junction AD and DA, here AD and DA, I have the linearly varying load, that is the trapezoidal load, 17,000 at the top and 36,800 at the bottom. For this linearly varying load, fixed end moment is PL square by 12 plus WL by 15. Right? So I will place this fixed end moments. At DC, I have 66,701. Next at BA, I have 26,208. At AD, I have 22,615. At AB, I have 53,088. Now balance it, carry over, balance it, carry over, and calculate the moments at every junction. DC 47,000 clockwise, DA 47,715 anti-clockwise, AD 36,608 clockwise, AB 36,608 anti-clockwise. So like this. At every junction, I have calculated the moments here. Okay. So now for horizontal slab AE carrying a load of 58,500 Newton per meter square, the vertical reaction at A and B I need to calculate. That is the shear force. At A and at B, I will calculate the shear force, and at A and at B, I will calculate the shear force. AD is subjected to UDL, right? Shear force is nothing but okay, WL by 2, 96,525. Similarly, for bottom slab, soil reaction is 73,500. Again, WL by 2. For AD now, AD member, for AD, I have to go for, since it's the linearly varying load we have, I have to go for the equilibrium equation. Consider the reaction at A, that is HA into perpendicular distance 3.3 plus the moments at every junction. Okay, 36,608 minus anti-clockwise is 57,715 plus 17,000. Like that, write down the equilibrium equation. Summation of moment is equal to 0. So summation of moment due to HA reaction is HA into the perpendicular distance 3.3. Right. So summation of moment is equal to 0. I have written, that is HA. I will get it, shear force at A. Next at D, the summation of moments I will get it as HD, right? Summation of moment at D is equal to 0. If I do, I will get HD. Both the shear force and moments I have got at every junction now, correct? Now, free bending moment at midpoint E. See, so since I am considering the half of the section, right? So same section will be replicating on the other side. Okay, at E, the net bending moment, since it is simply supported at E, the net bending moment is WL square by 8, 79,633, right? Net bending moment at E will be 79,633. Out of that, you have to deduct the moment which is at the support at A. So at A, it has gone to 36,000 something, and at B, it has come to 79,000. That means at E net bending moment at the bottom, how much you will get? 79 minus 63. If you do, you will get the net bending moment at E, 43,025 Newton. Now free bending moment at F at this central point. So I am calculating free bending moment to provide the reinforcements. Okay. So free bending moment at F is 73 WL square by 8. Out of that, deduct the end moment 47,715 at D. So you will get free bending moment. Now for vertical member AD, simply supported bending moment at midspan is WL square by 8 plus moment at one end minus moment at other end into L square by 16. WL square by 16. So load at one end, that is 36,800 minus 17,000 WL square by 16. That will give you net bending moment at AD for the vertical member. Right? So this completes the calculation of shear force and bending moments for the box culvert for load case 1. That is dead load, live load, soil pressure from outside, okay, no water pressure from inside. So this will give you the moments and shear force calculation. Okay. So for these moments, how to provide the reinforcements we will study. Now I have case 2 and case 3 examples. Okay, how to solve it. I will share this notes with you. Study case 2 and case 3. Take it as an assignment and solve it. Okay. So after solving for all the three cases, what he has done, he has tabulated the results for all the three cases. He has tabulated the results to note down the worst case here, right? Here, the top slab is subjected to these many values. For top slab, load case 1, bending moment only for top slab. This is not for side wall and bottom slab. For top slab, in load case 1, he has got the bending moment as 43,000. At ends, he has got it as 36,000, and shear force he has got it as 35,574. Okay, so in exams, only one load case is given to you. So you will get only one moment at center, one moment at end, and one is shear force. So he has put the table only for the comparison. He has solved it for all the three cases, the same problem. Okay. Now the section has to be designed for maximum bending moment. Okay. So out of all the three cases, it has to be designed for maximum bending moment. So we have got maximum bending moment in load case 3 here. Why? Because he has considered the surcharge load there. Water pressure is not there, but he has considered additional load there. Because of that, he has got the maximum moment in load case 3. But you need not worry about the maximum moment for all the three cases, because only one case is given to you in the exams. For that maximum moment, okay. For that maximum moment, we have the tensile force to 2117 Newton. Okay, the overall depth is 300 mm, not 30 mm, 300 mm. Effective cover 50 mm. I will get the effective depth as 250 mm for the box culvert slab. Okay, so effective depth required is m divided by J into D. That is working stress method. You have to calculate the moment constants M, Q, J, and D. Okay. 274.42 mm square is required for it. So we have provided 250 mm, right? So therefore depth provided is adequate. We have provided 300 mm, right? Next, area of steel is M divided by sigma st J into D. Correct. So 1224 mm square. So provide 20 mm dia, 250 mm center to center. Now these bars are bent alternatively near the distance of L by 5, okay, from the edges. So that detailing will go at the end. Area of distribution still is taken as 0.2% of gross sectional area. So 300 is thickness into 1 meter length, 0.2%, 0.2 by 100. So distribution still is 600 mm square. That is area on each face is 300 mm square we have to provide. That is two sides you will be having, top and bottom. Okay, so on each face it will be 300 mm square. So 8 mm diameter bars to be provided at center to center of 130 mm on each face to satisfy this 300 mm square. Next, bending moment at support 36. So area of steel required is 811 mm square. So we have already provided 20 at 250 at the center. The same steel I will be alternately bending it up at the support. So near the support I will be getting 1256 by 2, that is 20 at 215 is nothing but 1256 mm square. If I alternatively bend it, I will get 628 mm square near the support. So additional 811 minus 628, that is additional reinforcement shall be provided to satisfy this much of difference, that is 811 minus 622. Clear. Next, design of bottom slab. Same case. In bottom slab also, he has taken moments and shear force for all the three cases. So out of which is maximum, he has designed it. Again, you need not worry about all the three cases. In exams, only one load case is given to you. You have to design your bottom slab for the moment which you will get for that load case only. Okay. So effective depth required, area of steel required, right? So almost all the same steel you keep throughout your box culvert. So 20 mm on top slab if you have provided, on bottom slab also provide 20, and on side walls you can provide 16 or 20. Next, design of side walls. Design of side walls. Again on side walls, the moments and shear force carried out calculated are written here for all the three cases. He has taken the maximum moment here, okay, and he has calculated the mu by FCKBD square, nu by FCKBD square. Why? For this side, for top and bottom slab are designed as simply supported slabs, whereas the side walls are designed as compression members. Those are columns. So in columns, you will be calculating the percentage of steel required based on SP16. You refer see mu by FCKBD square and Nu by FCKBD square you calculate. So based on that ratio, you will get P by FCK 0.002. Okay, referring SP16. That is the design of compression members columns you have studied. Okay, so where percentage of steel is 0.02, FCK is 25. I will get P as 0.02 into 25. D dash by D I have calculated. Area of steel required for the side walls I am calculating 750 mm square. So area of steel required is 2 into 750 because on two faces you require the steel. See here, on two faces you require the steel 1500 mm square. But minimum reinforcement is 0.8% for columns, whereas for compression members. So 0.8% means I will get it as 2400 mm square. So this 1500 mm square becomes invalid. So you have to provide minimum of 2400 mm square in the side walls. So he is providing 20 mm diameter bars at 300 mm center to center on both the sides. So after calculating for top slab, bottom slab and side walls, provide the detailing something like this. See bottom slab, he has bent it up at L by 5. Bottom slab reinforcement. And in the bottom slab, he has invertedly bent it. So this will be the bottom reinforcement. Invertedly, he has bent it down here. Correct? And the side walls, he has given 28 to 50, 8 at 130 as the distribution reinforcement. It is a side wall is a compression member and top and bottom slab are the simply supported slabs. So this is how you should design the box culvert. So for load case 1, I have explained you. Take load case 2 and load case 3 as assignments. In load case 2, dead load, live load, earth pressure from outside and water pressure from inside. So additional thing is you have to calculate the moment and shear force acting due to water pressure. Right, so all remaining all remains the same. That is dead load, live load remains the same. Surcharge load, earth pressure load remains the same. You have to calculate the water load. So I will share this example. So load case 2 and load case 3 you study. So if you have any doubt, you can ask. Okay. Again, you have two problems here. You can take these as assignments and you can solve it. If anybody has doubt, you can contact me. Okay. Thank you.